So can we start, sir?
Yeah, sure.
Yes, sir. Yes, sir. So we are recording the program, sir. As per ATAL's rule, we are recording the program. Okay. So we can start now, sir.
Yeah, sure.
Yes, sir. So good evening, all of you. I welcome one and all for this ATAL-sponsored faculty development program on artificial intelligence-driven 5G 6G networks. We commence this FDP with the blessings of the Almighty. So to begin with, let me first thank the founders of this great WellTech institution, Colonel Professor Whale Dr. R. Rangarajan sir, founder, president and chancellor, and Dr. Sakuntala Rangarajan madam, foundress president, Mrs. Rangarajan Mahalakshmi Kishore, chairperson and managing trustee. They have provided all these platform and has facilitated us to conduct this ATAL FTP. So I wholeheartedly thank them. Next, I would like to thank Professor Dr. S. Salivagnan sir, Vice Chancellor of this University, and Professor Dr. E. Kannan sir, Registrar of this institution, and the advisors of this program, Professor Dr. M. J. Carmel Mary Belinda ma'am, Dean Academics, and Professor Dr. V. Jaishankar sir, Dean School of Electrical and Communication, Dr. E. Balasubramanian, Dean R&D, and also Dr. P. Chandrakumar sir, Dean Industry Relations. And in our institution, we have a world-class AI laboratory, and Chandrakumar sir has given us to conduct the hands-on sessions program of this FTP. And my special thanks goes to Dr. P. Esther Rani, professor and head of the department, who has been guiding us to bring this program a great success. And I acknowledge my co-coordinator, Dr. S. Uday Kumar, who has been working along with me to bring this program into reality. So to introduce about the institution to all the participants and for our prestigious speaker of the day today, WellTech is a great institution founded in the year 1997, and here we are adopting unique and trending educational methodologies. And also, we are the first member from India to be part of CDIO framework, which is an innovative educational framework for providing next generation of engineers. We are offering UG, PG and PhD programs in both engineering and management. And also, we have been recognized as the best engineering institution and ranked as first in India and 74th in the world by Times Higher Education World Young University, ranking to 2016 to 2017, and also 43rd in Asia by Times Higher Education Asian University Ranking 2017. We have Technology Business Incubator at WellTech, and it is recognized as a center of excellence under NITI by the Government of India. To say about a few words on our school, the School of Electrical and Communication at WellTech is imparting knowledge in electrical, electronics, and communication engineering and all other allied areas. The students of this school actively participate in various national level activities and bring out their skills in them. Many of the faculty members at WellTech University and the school are doctorates from reputed institutions from India and abroad. So to tell about our department, department is also founded in the year 1997, and we are NBA Tier 1 accredited in 2022. And we have well-equipped and state-of-art facilities for research and development. We have various laboratories like IoT lab, signal processing lab, and Xilinx powered system on chips laboratory, embedded systems, robotic laboratories and all supported by MHRD, and also IIT program and France Call laboratories in collaboration with France Call Technology, France. We are also initiative in alliance with international universities and core electronic industries and giving cardinal importance in the department. So I assure all the participants you are privileged enough to be a part of this FDP program at this prestigious institute. So with this good introductory words about the institution, department and our school, I once again wholeheartedly welcome the speaker of the day, Professor Dr. Shankar Prakia. We are privileged to have you, sir. When I approached you, you readily accepted. I'm very happy and so proud to have you in our midst. And we are very much awaited to hear your lecture. Surely, I assure all the faculty members, participants of this FDP will be benefited out of your speech. So today lecture is on introduction to AI in 5G 6G networks and its research challenges. Education is the most powerful weapon which can be used to change the world. Wisdom comes not from age, but from education and learning. I realize by being a teacher, I'm making an important contribution to all the national development initiatives. One such initiative is this FDP program. I encourage all the participants to make use of this opportunity and be benefited. I once again welcome the speaker, and after the introduction of the speaker by Dr. Anuja, professor from EC department, we will hand over this session to you, sir. Once again, I welcome and thank you for being with us. And once again, I welcome all the participants. Thank you all. Anuja, kindly introduce the speaker of the day, our prestigious professor, Dr. Shankar Prakia, sir.
Thank you. It gives me great pleasure to introduce today's eminent speaker, Professor Dr. Shankar Prakriya, for this first day session. Professor received the BE degree in Electronics and Communication Engineering from NIT Trichy in 1987 and MASc and PhD degrees from the Department of Electrical and Computer Engineering, University of Toronto, Canada in 1993 and 1997. Professor was with the Indian Space Research Organization for about 3 years. In 1997, Sir joined in IIT Delhi, where he is currently a professor with the Department of Electrical Engineering. Professor was the J. Gupta Research Chair Professor for 5 years until 2017. Currently, Sir holds the Chandramani Chair at IIT Delhi. Professor holds 3 US and some Indian patents. He has published more than 100 papers in reputed journals. His research interests include wireless energy harvesting, battery energy management, massive mission type communication, backscatter communication, and full duplex communication. Professor is a senior member of the IEEE. He is a serving editor of the IEEE Transactions on Wireless Communication. Sir, now the session is yours.
Oh, thank you very much for your kind introduction. I'm very happy to join this FDP.
Yes, sir.
Yeah, sure. So,
sir, actually, this session starts from 7 p.m. to 9:30. And first session will be a 50 minutes thing. And after 5 minutes break, the next 50. And the last half an hour will be on discussion. Oh, so sure. The time is yours, Professor.
Yeah, sure. You just let me know in case I've exceeded the time.
Yeah,
right? Sure.
Yeah.
So, okay. So, welcome all of you. I'm Professor Shankar from IIT Delhi, Department of Electrical Engineering. And I'll be speaking on energy and spectral efficient. I'll switch off the video. Yeah, so I'll be speaking on energy and spectrally efficient signaling for beyond 5G and 6G communications. Right? So before I start, a little bit about my research interests. I think this has already been mentioned. I have been working in recent times on non-orthogonal multiple access, interference management, D2D communication, battery energy management, cognitive radio, buffer relaying, backscatter, and intelligent reflecting surfaces, and massive machine type communication. Right? So I'll be touching upon some of these topics, and some of the work that is presented here constitutes the research doctoral work of some of the research scholars like Dilip Papatla, Anandji, and Mayank Gupta, and so on. Right? So there is also a DST SERB project on non-orthogonal multiple access and massive machine type communication, which sponsored some of this work. Right? So I thought I'd give you an overview of the work that I have been doing. So the team has been doing. Most of my students, as I told you, work on non-orthogonal multiple access and energy harvesting these days. So this is the work that is accepted the last 1 month or so. So this is mostly to do with non-orthogonal multiple access. And the first one talks about underlay communication, in which we have a new method of combining at the users with NOMA. The second one in the IEEE Journal of IoT, it is on energy and spectral efficient AF relay aided incremental CDRT. And the third one is accepted in the IEEE transactions of wireless communication. It concerns again non-orthogonal multiple access, in which we propose a new scheme to manage the interference and also to allocate the power for various near user and far user. The last work is on FTD, full duplex D2D communication. This is the work of a research scholar, of an MTech student, built up by a research scholar. The first one, also Deepali, is an MTech student here. This was Suraj is also an MTech student. In the past, I've worked a lot on energy harvesting. As you can see, this is slightly older work, 2018-ish work. So a lot on energy harvesting. We developed a new method for battery energy management using energy harvesting. So I'll be discussing that a little bit today. So I'll be touching upon various topics, which I think is good because it will give you an overall flavor of the type of problems that we're tackling. Right. So both of these, this energy harvesting. The last one is an underlay cognitive radio and energy harvesting. This again is slightly all this again is built up on the same work, energy harvesting type of work. Right. We have a granted US patent on this, on battery energy management. We also worked a little bit more on energy harvesting with energy buffers. Right. So we developed a proper mathematical framework for management of energy buffers with using a continuous state Markov chains. I'll talk a little bit about it. Okay, so then a little bit more work. This again relates to energy harvesting using buffers. In the last work, which appeared in Journal of IoT, the second work, we talked of energy buffers and data buffers and how to balance both of them. Right? So this is because when you're storing energy or you're storing data, but you cannot store endlessly, right? You balance the buffer. Right, so buffer as input and output, but to balance it. So this is what the paper is about. We also have some other work on non-orthogonal multiple access. The first one concerns IoT networks in which there is energy harvesting, which is used for forwarding information in a cooperative framework. Right, so the first work that has appeared of this particular sort using energy harvesting, energy buffers for non-orthogonal multiple access. This is slightly older work related to cognitive radio. In the past, I told you I had worked on cognitive radio. We had a Media Labs Asia project in which 2-3 students had worked on various aspects of cognitive radio, multi-hop relaying in underlay networks, buffered relaying in underlay networks, more work on energy harvesting and underlay networks. And we here worked a little bit on secrecy in underlay networks. The last two works relate to secrecy. So I told you slightly older work, and this is of course again buffer relay in the underlay context, and this is about secrecy, how to ensure, trying to show that allowing multiple users to transmit improves secrecy. And this is again, yeah. So this is more recent work. We have worked on energy harvesting and full duplex relays. The second work is a non-orthogonal multiple access with battery assisted energy harvesting relays. And so I'll be talking a little bit about it. Maybe it will make sense for you. The first work is a non-orthogonal multiple access, only a letter item, but we show something very interesting. We show how we can improve the performance of a distant user without sacrificing the performance of a near user. Right? This is interesting. We have filed a patent. This Nagajanth was an MTech student here. Along with an MTech student, we had filed up for a patent on semi-grant free communication using non-orthogonal multiple access. More work on non-orthogonal multiple access in recent times. I think this is relatively very new. So we showed that in underlay networks we can have non-orthogonal multiple access. We showed this for the first time and how it can be made to work. Then the second work we published in Transactions and Communication just a few months back. It relates to a new framework for non-orthogonal multiple access, right? To ensure good performance at near user and far user, right? To get a so we'll be touching upon this a little bit today. The last work concerns underlay cognitive radio, in which you're trying to have uplink communication by more than one user. This again slightly oldish work, but it relates to interference management. It worked on how to manage interference in a cellular network, how to ensure higher secrecy in a cellular network. The second one. We also had some patent application on mode switching, etc. in such networks. But this gives you a flavor of the type of things I've been trying to do in the last 4 years or so. So before I start off, I'll try to I've been dealing with say various communication terminology, right? Many of you I think are already working on communications, you may be familiar with it, but it is still good to have introduce some of these performance metrics that we are going to talk about, right? So I'll be talking about a little bit of communications. I'll be talking about analysis of performance. Then I will talk about how some deep learning techniques can be used in communication. And one example at least we will take. Right? So to start off, this if you y equal to square root of p into h into x plus n is an expression of the sampled match filter output. Right? If the power is p, your x is a symbol, and n is your additive wide Gaussian noise, then y is what you get. But h is the multiplicative noise or fading that you find in all wireless communication. Right? So the point is, what is the signal to noise ratio? It is p into absolute value of h square divided by the power spectral density of the noise. I'm taking it to be complex. I wrote it as n naught. That is not the point. The point here is that the signal to noise ratio is a random quantity because the channel is random, right? At any given point of time, absolute value of h whole square is a random quantity. So the signal to noise ratio becomes random. So the quality of service keeps on changing. Right? Channel realization to realization. In one coherence interval, it remains fixed, but next coherence interval it changes. Right? So when that happens, you need to have proper performance metrics. And of course, you're all familiar with the notion of diversity. Why diversity is required? Because there's a random quantity taking small values. So if you have multiple antennas or you do multi-user selection, things like that, or frequency or time diversity, you can improve the performance. Right? But we're not interested in that. We're interested in defining terms like outage probability, ergodic rate, etc., which are important in such fading scenarios. Okay, so let us assume fixed state transmission at rate R. Hello.
Yes, sir. Yes, sir. You are audible, sir.
Okay.
Yes, sir.
So, okay, let's assume fixed state transmission at the rate R. Okay. So here I told you that the signal to noise ratio is a random quantity. It keeps varying like this. Okay. Now, when you are assuming fixed state transmission at rate R, you know Shannon's theorem, log to the base 2 of 1 plus SNR is equal to the rate. So let's assume that rate R is equal to R. So R is equal to 1 log to the base 2 1 plus gamma TH. Right. So now you work backwards and find out the threshold SNR. It turns out to be 2 power R minus 1 from Shannon's theorem. So you know that this is the SNR that you want. Right. But the SNR will be randomly varying and sometimes it will fall below the threshold, which means there will be outage. So in those channel realizations, no communication is possible at that rate R. Right? So the probability of the signal to noise ratio falling below the threshold required for communication at that rate is called the outage probability. Right? So I'm reviewing this because I want to point out many things with a very high probability, because suppose you take the outage probability to 10 power minus 3, then 1 minus 10 power minus 3 is the probability that the SNR is higher than what is required. This is very, very important to appreciate. Right? So we're going to utilize this when we talk of how to improve throughput, etc. in communications. Right? With a very high probability, for example, it is 10 power minus 3, then 99.999% of the time, the SNR is larger than what is required, and we can exploit that. Throughput, the non-outage probability multiplied with R, right? Then non-outage probability multiplied with R, and of course the outage also is P0 is a function of R, so you have to optimize it with respect to R. Basically, it's the number of bits that are able to successfully communicate to the destination on the average. Okay, I think all of you are familiar with ergodic rate. Suppose you look at a channel with an SNR of gamma SD. I told you that gamma SD is a random quantity. So the instantaneous capacity will be locked to the base 2 of 1 plus gamma SD, 1 plus SNR. But this is a random quantity, so it does not make sense because there you have to take an expectation ensemble average, and you get an ensemble averaged value, and that value we call it the ergodic rate. So it's useful when you are using adaptive rate transmissions. Right? That means you're changing the rate to suit the channel. Okay. A little bit about relays, because I might talk about relays here and there. In some, it will come up. In such cases, we should know what a relay is and what it does. So you have a source, you have a destination, you have a relay in between. So if you communicate directly from the source to destination, there is going to be path loss. I think all of you are familiar. The square law, at least, right? So which means that the received power keeps on decreasing very rapidly with distance, which means that the quality of service at the destination will be very, very poor. So we use a relay in between. What does the relay do? It takes the signal from here. This distance is very small comparatively. Signal to here, the SNR will be reasonably good. So you decode that information and you transmit it to the destination, and you can combine these two. Right? So normally when you talk of relays, you say relays are needed because of path loss. You want to improve the signal to noise ratio. One aspect that is ignored and we don't think about too much is that relays are required to control interference. Think about it. When you have an LTE where the frequency reuse factor is 1, then suppose you think of your source as a mobile unit. You want to communicate to D, which is your base station. You're at the edge of the cell. This is at the center of the cell, and the huge distance is huge. So you have to transmit with large amount of power. If you transmit with large amount of power at the cell edge, you will cause a lot of nuisance to the neighboring cells because frequency reuse factor is now 1. You're using the same frequencies in all the cells, right? Which means that you must decrease your transmit powers whenever possible. So you cannot allow a user at the cell edge to transmit with high power, right? So that is why a relay is required. If you have a relay, then you communicate with much smaller power, and the relay can still decode and communicate to the destination. So relays are required for interference management. Right? The other reason why relays are required is because you want to, many of these devices are battery operated, right? You cannot afford to transmit with large amount of power. If you transmit with large amount of power, your battery gets depleted very fast and it is inefficient. So energy efficiency is the issue, right? Relays are required to improve energy efficiency. Okay. I will be touching upon various topics. Right now, you will not see the connection between various topics, but all this will make sense when I tie it all together later. Right. So I will talk a little bit of cognitive radio and the type of ideas that came from cognitive radio. I told you that earlier I had worked on cognitive radio a little bit, and some of the ideas that we developed in cognitive radio were applied it to 5G communications and so on for power control and interference management. So I'll be talking a little bit about that. So it's good to have some kind of a basic introduction to cognitive radio. What is cognitive radio? I think all of it arose maybe in very early in 2000 or so, where people started talking of spectrum crunch, right? And most of it they found out was because of inefficient use of the spectrum. Right? What's happening is a big band of frequencies, big frequency band was allocated to one particular operator for one particular use and over a large geographical area, right? So sub-licensing was not allowed, and you cannot change the service for which it is allocated, which means that spectrum is very poorly utilized. Okay, this figure in itself doesn't convey too much, but what they did, they studied the frequency band from 700 megahertz to 1 gigahertz, very commonly used frequency band, right? So you expect a lot of activity, right? This is allocated to various services. Here in this figure, you don't have to worry about the details, but wherever it is light, it means it's very lightly used, and when it is dark, it means it is heavily used. So you will notice that in this entire band, which is supposedly very highly used, you find that most of it is lightly colored, which means that it is not being effectively utilized, right? So people said that spectrum is not being efficiently utilized, and that is the problem, and not the non-availability of spectrum, right? So people started doing various things. So I think one of the things you might be familiar is that they looked at TV white space, the space that is frequency bands that have been vacated because of digitization of TV, right? We no longer use those TV transmitters, so those bands can be utilized for data transmission. So I think white space radio was invented and used and studied quite extensively, right? Some countries utilized it very, very well. In US, it has been utilized for providing service, right? So in different geographical areas, some TV stations might use the band, sometimes they don't use at some points of time or on some geographical locations, and those can be utilized. Okay. So I think some things of this we can skip. Right, we'll talk a little bit about traditional cognitive radio. I think all of you, many of you would have come across this cognitive radio. So the basic idea is like this. We are saying that the licensed user, we're going to call the licensed user the primary transmitter, primary network, the primary transmitter and the primary receiver, right? We're going to say that, yes, it is not effectively utilizing the spectrum. So whenever it is not utilizing the spectrum, why not allow one other network, the same geographical area, to use it, right? That will improve spectrum utilization efficiency, right? So that seems like a logical idea. So how do we make this work? The traditional idea of cognitive radio is like this. You have the secondary network along with the primary network, which is a licensed user in the same band, right? In the same geographical area. So what you do, a secondary transmitter will try to do spectrum sensing, try to check whether that spectrum is being utilized or not in that particular band. And when it is not being utilized, it can transmit to a primary receiver, right? Sounds nice in theory, but it has never been utilized and never became practical reality, except in some cases. No, white space, I told you, in US they had utilized this white space radio, but it could not be utilized on a large scale simply because of the fact that spectrum sensing may not be entirely reliable. And suppose there is some building blocking the path between the primary transmitter to secondary transmitter. The secondary transmitter might think the signal here might be weak, and it might think that nobody is transmitting that band and start transmitting and can cause a large amount of interference. There's also the security issue, right? If we allow nodes to transmit in the same band, they might actually intentionally also transmit using large amount of power and create chaos in the network, right? So it's a security issue. So for these reasons, this type of cognitive radio never really took off, right? Like it was expected to in early 2000, right? Spectrum sensing was studied very extensively and many people worked on it. A different type of cognitive radio, however, has found utility in modern networks, right? So the way it works is like this. The basic idea is that, okay, the received power keeps on decreasing with distance, and the noise level is like this. So as long as, suppose you say that we allow a certain amount of interference, all it means is that the noise floor has increased and therefore the coverage area has decreased a little bit. Suppose they're willing to sacrifice that, then we can tolerate certain amount of interference, right? So let us look at it like this. We allow a certain amount of degradation, let us say an outage probability. Let us say outage probability of 10 power minus 2 is acceptable to me. Then what I can do, I can allow a certain amount of interference until the outage probability becomes 10 power minus 2. Similarly for ergodic rate and such things, right? So now look directly at this. I have a primary transmitter, I have a primary receiver. The channel is H, okay? And I have a secondary network in the same band, right? Notice that you're not doing any spectrum sensing here, right? You're not doing any spectrum sensing. You're transmitting even when the primary transmitter is transmitting at the same time. Concurrently, you're transmitting, right? But you control your transmit power intelligently in such a way so as to not cause severe degradation in the primary receiver. How is that possible? What's the basic idea? The idea is like this. The channel between the primary transmitter to primary receiver is a fading channel, which means that there is a fading channel H, right? It's a random quantity, taking small values with high probability. I told you that if I fix the outage probability to be 10 power minus 3, then 99.999% of the time, this SNR is going to be larger than what is required. I hope this is the reason why I was stressing on it, right? If this SNR is going to be larger than what is required, then it can tolerate certain amount of interference, is it not? If the SNR is larger, let's say SNR is 30 dB, but I only want 20 dB, then I can tolerate 10 dB of interference, right? I hope you're able to pick up the basic idea. The idea is that this SNR is going to be larger than what is required simply because of the fading nature of the channel. We are exploiting that and saying that yes, it has the ability to tolerate interference. Let us then allow a certain secondary transmitter to cause interference equal to some value IP. Okay. Example, I was telling you 10 dB or so. Now, if you have to cause an interference of 10 dB here, your transmit power has to be adjusted. What should be a transmit power? Forget this max and Pmax. PS should be IP by G absolute value whole square, because PS into G absolute value whole square, suppose this is PS, into G absolute value whole square is equal to the interference caused at the primary receiver. And that should not exceed IP, right? You keep that in mind, you will understand why this type of cognitive radio is very, very advantageous, right? Because you're exploiting the fading nature of the channel here. Here also you're exploiting the fading nature of the channel because you know that G is a fading parameter and it is going to take small values with a high probability, which means that suppose you have multiple secondary transmitters, you can always pick one which has got a very weak link to the primary receiver and therefore can transmit with high power without causing undue interference to the primary receiver. This is why it's a powerful idea, right? This is the reason why underlay cognitive radio has the potential to exploit something called spatial holes, and not just spectrum holes, in order to dramatically increase the spectrum utilization efficiency. Okay. So this interference threshold, the amount of interference that you can call, that is called ITL, interference temperature limit. It can either be a fixed quantity or it can also say, okay, the channel is fading, so my tolerance to interference is also changing, and I can do it both ways, right? So the primary channel is extremely good, then I have larger tolerance to interference. The channel is very poor, I have less tolerance to interference. The channel is very, very poor, then the SNR is so poor that you cannot tolerate any secondary transmissions and you have to switch it off, right? So this is okay. So far we have been talking about some elementary stuff that we'll be utilizing. So now going to the topic proper, I would like to show you one set of figures that are drawn from a tutorial article on 6G from an IEEE magazine article. So it shows you the evolution as you go from 1G to 6G. What are the things that happened, right? Of course, they're all familiar. In 2G, you had text and a little bit of voice. Then you had talked of in 3G, we talk of multimedia and voice. And 4G, we talk of mobile internet and so on. And 5G, very different. See, these things are all very different. You're talking about smart cities. In 6G, you're talking about entirely different stuff. In Internet of Bio, nanotech things and so on. You're talking about very different things. Right? Automated cars and so on in 6G. So the applications are changing quite a bit. Now, what about the key performance indicators? I think all of you are familiar that what has changed when you're going from 1G to 6G, right? You find that the peak data rate has increased tremendously. In 6G, you're talking of peak data rate of 1 terabit per second, right? It is 20 Gbps in 5G, right? So you're talking about huge increase in peak data rate. You're also talking of huge increase in mobility. That means your ability to transmit or receive when traveling at a very high speed, right? In 6G, you're talking about 1000 kilometers per hour speed. In 5G, you're talking about 500 kilometers per hour speed. You're talking of very decreased latency, very small latencies as compared to the past. Right? This becomes important when you have gaming and other type of applications. Latency has to be low, right? The other thing, maybe the important stuff is here, right? The number of devices per square kilometer in 3G it was just 10,000. In 5G it is larger. Sorry, in 4G it is larger. In 5G it is 1 million. 5G has to provide for 1 million devices per square kilometer. In 6G you're talking about much larger number, right? 10 times that or more, right? So how do we get so many devices per square kilometer? Obviously, they're not mobile units. They're all going to be IoTs type of devices, machine type devices. That is why you get such large number. These are required for smart cities and other applications. This is where AI becomes very important, right? Because the number of devices has increased by a very large amount, right? Then if you look at traffic volumes, megabit per second per meter square, 1 meter square of area, what is the on the average that the megabit per second? It turns out in 6G you're talking about 1000 megabit per second per square meter. Right? That's a very large. Traffic volume is very large, and spectral efficiencies you're talking about is 15, right? Which is very large. Even in 5G you're only talking of 3 times the earlier one. You're talking about 15 times the earlier one. So that is a huge increase in spectral efficiencies. Right? And it is being obtained obviously by frequency reuse and careful interference management. The energy efficiency also is increasing by a large amount. The amount of energy that is being used by 4G stations is also very small, but 5G will be even smaller, and 6G it will be even smaller because the cell sizes will become smaller, right? And you're going to communicate over shorter distances. The powers used to be very small. Okay. Network characteristics wise, if you go from 1G to 6G, you can see all this, right? I hope we are able to appreciate. In 2G, you're talking about circuit switching and packet switching. Then you're talking about very different things when it comes to 5G. In 6G, you're talking more of intelligence and so on. When you talk of evolution of technologies itself, so in 5G, you're talking of non-orthogonal multiple access. You're talking about rate split multiple access. You're talking about massive MIMO and so on. And in 6G, you're talking about very different things. You're talking about AI, machine learning, and reconfigurable intelligent surfaces. I'll be touching upon this a little bit today. So these as we are going towards 6G. So what are the things that we see? We see that there is a tremendous increase in the number of devices per square kilometer. Right? That means the number of devices is increased, which is something you have to keep in mind. And the power consumption also becomes very important, because when you're going to have 10 million or 20 million devices per square kilometer, obviously we cannot keep changing the battery of all these devices. The batteries have to last a very long time, right? So energy efficiencies become very important, and your spectral efficiency of course has to increase, but the number of devices has to increase, which is a very different thing, right? Your ability to provide service to a very large number of users is very important. So in the initial parts, I talked a little bit about energy harvesting, the work done, right? So I think all of you are familiar with limitations of battery technology. So what are the problems with batteries is that batteries do not last as long as you would like them to last. All of you, I think, see that when you have mobile devices, your battery seems to run down very, very fast. But in the case of IoTs, you need to have the battery last 10 years as per the standard of 5G. 5 to 10-year battery lifetime has to be guaranteed, right? This is going to be pretty tough, right? To guarantee a lifetime that is so large. So, but battery technology has not kept pace with improvement in communication technology. So certain things need to be done. We're going to see later that the way the signal has to change as we move towards 6G. That also will touch upon a little bit. So battery replacement is a problem and we cannot keep on charging. So there has to be something new that has to be done. I think we need to work towards batteryless type of self-sustaining devices. The reason is that if they're batteryless, they can last theoretically forever. The second thing is that if they are batteryless, the size of the device will be smaller. They'll also be cheaper and they can employ much larger number of devices, right? So making the devices batteryless, it should be the ultimate goal and it will happen before 6G. Self-sustaining devices that simply harvest energy from the environment in some fashion and then use it for communicating data, right? So how do you harvest energy? You do it from light, temperature difference, pressure, vibration, and so on. Doing it from RF seems to be the most sensible option. So wireless energy harvesting from nearby power sources is even more sensible and reliable, right? Than hoping for some ambient RF from FM bands and so on. Right? So energy can be transferred from a dedicated power beacon, for example. In one particular, so if you have an OFDM system, one carrier I use for power, so all neighboring devices can get power. So energy also can be scavenged from ambient RF because there'll be communication nearby. You can scavenge from various bands and use it for communication in your own band, right? So simultaneous information and power transfer is being studied a lot. And that is one way in which I'll be talking a little bit about this. So the central idea is that the battery lifetime goals of 5G in NB-IoT and other type of technologies, it is very, very large and it is not possible to meet these energy efficiency, this lifetime goals unless we do something different. Right? The way we signal and the communication protocol has to be different. The way we manage the energy has to be different. So energy harvesting seems to be the way, but there are problems with energy harvesting. One of the ways is that, the amount of energy that is harvested is typically very small. Okay. For the communication that we need to do, suppose we need to do RF signaling in a particular band, the amount of energy that is taken away by the RF chains is very, very large. It becomes inefficient. If you take a large amount of power, but the amount of energy that you harvest is a random quantity, and also on the average, it's a small averaged value. So there is something needs to be done to deal with it, right? So we looked at this and said that, okay, I think okay. So we looked at it and then said that, if the variability is the problem, maybe in the immediate future, we don't try to get rid of batteries, but to keep batteries, but you use the energy harvested, and when you fall short, you take that remaining energy from the battery so as to increase the battery lifetime. This is what the patent was about. Different ways in which the battery energy can be managed. That means you're adding very small amount of battery energy to the harvested energy so as to maximize the battery lifetime. Okay. So the other thing that you can do when there's large variability, what do you do, right? When there's large variability, one other thing that you can do is to store the energy, right? The moment you keep storing, then the variability will reduce, right? This is what you do when you have variable income. Every month, your income, let us say, varies by a very large amount. Sometimes you earn lakhs and sometimes you earn thousands. And what do? Obviously, all your money that you get, you put it in a bank, and from the bank, you draw a fixed amount of money that's equal to slightly less than the averaged value of the energy of the money that you're earning, right? This is a sensible thing to do. If you do that, the variability is reduced and the performance, QoS, quality of service will improve. So both these are very important. We looked at both these things, right? So supercapacitors are used for store energy in wireless energy harvesting, which are typically poor. 60% energy efficiency is what you can get. So typically, and you cannot in a supercapacitor, you cannot store the charge or harvest energy and store it and also draw energy at the same time, right? There's a half duplex constraint. Either you're charging the supercapacitor or you're drawing energy from the supercapacitor. You cannot do both simultaneously, which means that certain techniques are required. That's why we do time switching and power splitting. In time switching, for a certain amount of time you can charge and then you do perform communication. In power splitting, you're taking the signal, you're splitting the signal, received signal into two parts. One part you're simply harvesting, the other part you're doing decoding. Right? So these are required because the same signal cannot be used for information decoding and energy harvesting. It is not possible. So I will skip these time details. Maybe you're all familiar with this. So this is what I was saying. There are two things that you can do. The battery assisted energy harvesting is what we studied first and showed that adding a small amount of battery energy from the battery can significantly improve performance. And therefore, in the immediate future, it is a possibility because up to now, there are very few self-sustaining type of nodes, IoT nodes that don't require any battery. Right? Such things are still being developed by various companies are looking to develop these things, but still they cannot provide reliable service because it takes time to accumulate the energy that is required for transmission, and that becomes a limitation. Right? I will say later that yes, the way your signal can change, and that can actually be a game changer. Right? We'll come to that a little bit later. But right now we look at these two approaches: battery assisted energy harvesting and energy buffer approach. Okay, the very basic idea of battery assisted energy harvesting is very simple. For alpha t, fraction alpha is a certain fraction less than or equal to 1. So certain fraction of the duration, signaling duration, I can do energy harvesting. Then I can add certain amount of battery energy from it, EV. I can intelligently choose the value of EV, and that is my energy. And the rest of the time, 1 minus alpha t by 2, I divert it. I can receive the signal and I do information decoding. Right? A very simple thing. The question is, how much energy should you draw from the battery? Right. So this is what it is about. Similar thing can be done for power splitting. So we published a series of articles, papers on this. Most of them appeared in Transactions, and one I think in Systems Journal. So that showed how you can, such a simple idea can be very, very effective. Right. So I'll just draw upon this. So we have a system, let us say it's an access point or something, multiple antennas. This is a relay. This relay is maybe an IoT type of device, which obviously doesn't want to utilize its battery to relay to a destination because this destination is too far away. We cannot communicate to a destination, but we can communicate through a relay. The relay does not want to use all its battery energy to perform relaying. So what it does, it performs energy harvesting and then adds a little bit of battery energy when it is required. Right? This is the basic, this idea. And obviously, when you have multiple antennas, you can perform some kind of beamforming and then you can harvest the energy here. So don't have to go into the equations, but we will see that if you have, this is a signal to noise ratio and this is a throughput. OK, so if you don't use any battery energy, the throughput I'm getting is really very small. Even at 35 dB, you're getting very poor throughput of less than 0.5 or 0.5. That is exceedingly poor. But at the same 35 dB or 30 dB SNR, if you add a little bit of battery energy, it might just be a microwatt per symbol, but you will find that huge improvement can be there in throughput. Dramatic improvement in throughput takes place, but only in this range. You see, when the SNR is low, then adding a small amount of battery energy can dramatically improve your throughput. Right? Which means that you can have serious savings in battery energy, right? And you can get much better performance. And obviously you need to choose your parameter. That means how much of time you're devoting to energy harvesting. That has to be optimized. If you devote more time for energy harvesting, then you can draw less amount of battery energy. So this thing we have brought out here, for example, alpha is a fraction of the time you're devoting to energy harvesting. So obviously, if you devote more and more time, for example, this is so alpha is so very large, then we're supposed to start putting certain amount of battery energy, then you can decrease the amount of time that you're devoting to energy harvesting. Look at EV equal to 1, the amount of time devoted to energy harvesting can be reduced. If EV equal to 3, you're practically devoting all your time for signaling and you're not wasting any time in energy harvesting, right? We also showed how the battery energy consumption can be minimized. Right? For a target throughput, we show how we can, choose your parameter, harvesting time, battery energy, etc. in an intelligent fashion. This is, for example, a plot of EB versus alpha. And for all these are contours of the same throughput, So as you can see, at all these points, that means different combinations of EB and alpha, they're all giving the same throughput, you see. These curves are all same throughput points. So that means that a certain value of alpha exists at which the battery energy consumption is minimized. So that can be done. To use time switching or power splitting? That is a question, right? So it turns out that time switching is easier, power splitting is more complicated circuit wise, but power splitting gives you better performance. And what we showed here is that if you're going to do battery assisted type of thing, then it can turn out that time switching actually performs better. It's a very interesting thing. So we looked at various things and we showed that energy consumption wise, you seem to be better off with time switching because less energy consumption, we're getting the same performance compared to power splitting, which is rather surprisingly different because it's always assumed that power splitting is better. It is not the case, really. OK, can skip some of these, not required. We also looked at two-way signaling in this context. Let's skip this. We also looked at full duplex signaling. This work appeared recently. So we have full duplex relay in between. Then you have a source, full duplex relay, and destination. And this is doing energy harvesting. Battery assisted. We also looked at non-orthogonal multiple access networks in this context. Then I was telling you the other thing that you can do when there's a lot of variability is to store it, store the energy and then transmit. So this is a relay. Relay here is an IoT node. It is storing the energy. Then it is transmitting to the destination. So when you do such energy harvesting and transmission, obviously I told you there is a half duplex energy harvesting. When you do energy harvesting, there's a half duplex constraint, which means that you cannot harvest and then draw energy at the same time. So what you need to do is to have two buffers. One is secondary energy buffer, which is actually doing the charging. And there is a primary energy buffer where the energy is stored. And when you want to transmit, you draw energy from the primary energy buffer, right? Which makes sense, right? You have two supercapacitors. One of them is charging, the other you are drawing the energy. That is the way it works. At the end, after finishing, it will just transfer the energy to the primary energy buffer. So that is what we do. And what we showed, see, normally when you do energy buffers, all of you may not be familiar with it, but we use something called discrete state Markov chains to model the energy buffer. So you put finite number of discrete levels, and then you try to find out the probability of occurrence of various levels, energies, and occurrence of various states. That means various amount of energy being present, and use that in order to estimate the performance. It turns out that this doesn't work very well at all because energy is a continuous parameter. Then we showed that we can use continuous state Markov chains. I think all of you may not be familiar with it, but discrete time, but continuous state Markov chains. And then we try to show that we can actually accurately model the performance and get much better idea. And then we showed that the way the performance that you get depends on how you manage the energy buffer. Look at this, something called on-off policy. What you do here is that suppose I require a certain amount of energy, M units of energy to transmit. If the buffer will have various amount of energy because it's harvesting and transmitting and so on, right? So you don't know if the buffer has got more than m units of energy, then you transmit. Otherwise, you keep quiet. Keep quiet means that time you are just the buffer, you're simply adding the harvested energy. If you're transmitting from the buffer, you subtract the energy that you're using for transmission and then add the amount of energy that you're harvested. So this is the way it works. So this policy is very different, right? But now there's a different policy that is possible. Whenever the energy that you're harvesting is greater than a certain value, transmit. If the energy is less than a certain value, transmit again. But with that, whatever energy that you have, that means you clean up the buffer, use all the energy and transmit it off. So this is also sometimes works better. What we showed is that there are some situations in which this energy management technique can give you much better performance than the one we talked about earlier on. So I don't think we should get into the maths of it, which is not of importance. But you can look into the maths. If you can look into the paper if you are interested. We showed that you can get an expression for the density function of the energy and use that in order to characterize performance. We showed that the buffer size is small and what happens in the buffer size is infinity and so on, and compare it with the case when there is no buffer and so on, and showed that you can get large improvement in performance. This is for outage property. You get large improvement in performance provided you have an energy buffer. It is intuitive, right? If something is randomly varying, then storing it makes sense, right? So this is what we showed: throughput versus distance. Maybe this some curves I can possibly skip. Because some of you, I think, are from AI backgrounds. It will be nice if I can go to the topic proper for you. Right? So energy buffer. It turns out that maybe I will just go to the incremental type of thing. I don't know how many of you are familiar with incremental signaling. But what you do in incremental signaling, you go back to this figure, maybe I'll explain it to you. Sorry for that. Yeah, what you do here, I think those of you are interested in physical layer communication, you try to communicate from the source to destination. With a certain probability, it will work. You're able to communicate successfully, you get a flag saying yes, packet received. Suppose it says packet not received, then what you can do, whatever the relay has decoded, you can forward it to the destination. If the packet is received, then you transmit your next packet. This is called incremental signaling, right? Because you're getting a flag from the destination, you can send a new packet or send the same packet from the relay. If you're sending the same packet from the relay, it's a waste of time because you're wasting 2 time slots to get to the destination. If you're sending in a single shot, if it is possible, then it is wonderful because you're saving energy and so on. But here, because it's storing energy, the things change, because if you're not transmitting, that whatever energy that you're harvesting is getting saved and that energy can be used later. Right? So this is significant. I hope you're able to appreciate that in all those intervals in which you're not transmitting, you're actually accumulating energy and that can be used in the future. That is why it works very well. And we showed that if you use the best effort BEP policy, energy buffer policy, you can actually get a diversity advantage. I'll show you that. I think all of you may not be able to appreciate, but those of you who have done wireless communication will see having a diversity advantage is a big deal, right? You can get a huge advantage in terms of diversity. We also looked at full duplex communication in this scenario, and I will not go into the details. We also looked into this type of situations, right? A lot of IoT nodes are there which are energy harvesting. There is a reader, right? There's a reader which is reading this IoT data from this IoT nodes, and then it is communicating to the cloud, right? So when you're doing such things, you will notice that these are energy harvesting devices, and therefore your data rate here is very, very low. This is an unreliable link. From here to here, it's a powered node, therefore the data rate can be high, and it's a reliable link. That's very important to understand. So does it make sense to transmit from here to here? Next time frame transmit from here to here? It is not really the case, because here the data rate is low, here the data rate is high, and this is reliable. So what we said is that you can communicate, you keep on communicating from the IoT node, energy harvesting IoT node, to the data collection point or the relay. And whenever this transmission is not possible, you can send a packet to the destination from the relay at a very high rate. Right? So, and then obviously it means that you have to store the data, right? So you have a data buffer and you have an energy buffer at the source. How to balance both of these and make sure the buffer doesn't overflow and so on. How to intelligently manage both these buffers. So is what this paper was about. It appeared in the Journal of IoT. We also looked at, I told you non-orthogonal multiple access. I think I don't have the slides, but we also looked at non-orthogonal multiple access using such devices, energy buffers, and showed that there can be enormous improvement in performance in practical systems simply by storing the energy. OK, the other thing I was telling you that with current technology, if RF chains are going to take away most of your energy for transmission, right? It is not practical. You cannot harvest energy and then transmit with it simply because of the fact that the energy required for transmission is very, very large. That happens because RF chains are taking away most of the energy that is required. The RF chains cause most of the wastage of energy, right? So the trick seems to be energy efficient signaling. We need to do something different, right? So those of you are interested in research ideas, you can pick up. There's something called media-based modulation. There's something called load modulated arrays. The way they work is very different. They don't try to they decrease the number of RF chains, right? And they still get very good performance. Right, so, but I will not talk about that. We'll talk a little bit about backscatter communication because that might also of interest. The key idea seems to be here is that you don't have RF chains. You cannot transmit, but you can reflect, right? That is what backscatter communication is about, right? You have no RF chains, therefore you don't require much energy at all. All you're doing is simply taking the signal that is coming and then you're reflecting either a lot or not reflecting, not reflecting. So how do you do that? I think all of you are familiar with this. If you have an antenna and you have a matched load, then it transmits, then it receives. That if you intentionally mismatch the load, obviously it's going to reflect. Right? So all you need to do is to have something like this. You have an antenna, you connect a load Z1 and a load Z2. Z1 is perfectly matched, so all the energy that is coming from here will get absorbed. If it is not perfectly matched, then it will get reflected. So if you want to transmit a 1, so you transmit a 1, then you mismatch it. Signal gets transmitted out. You want to transmit a 0, you perfectly match it, nothing will get transmitted. So on-off keying is possible. Similarly, you can use complex impedances and you can have change in phase. So BPSK type of signaling is possible. I hope you're able to see how this works. This is how RFID works anyway, right? You have an RF source, you have a backscatter device, and all you're doing is changing the load. And changing the load does not require a huge amount of power. As you can see, there is no RF chain at all. You have no RF source and you have no RF chain. All you have is an antenna to which you're changing the load, which requires very small amount of power. So just with microwatts of power, you're able to communicate. Right? This is a big deal. This is what I was saying. Backscatter communication is energy efficient, and you can, therefore, is the way to go. Just with 10 microwatt of power, people have been able to demonstrate backscatter communication, which means that because the range of energy that is harvested is roughly around this range, it means that we can actually have communication that is powered by energy harvesting. That means the way we are signaling has to change, right? So RFID, I think all of you know, you have an RF source, you transmit, and you have a reader attached to it, and it gets back a signal, and you're getting back a signal because in the form of data. It is saying that when you want to transmit a 1, you mismatch it. When you want to transmit a 0, you match it perfectly, so nothing gets reflected off. So based on the reader will decide whether this backscatter device is transmitting a 1 or a 0. And similarly for BPSK and other type of signaling. So obviously, this type of devices, some devices can sometimes be passive, but sometimes you can also harvest the energy that is coming from there, right? Rectify the signal that is coming from here. use that harvested energy in order to communicate. That's also possible. The range is, however, very small. RFID, I think all of you know. But backscatter, what is done is the RF source and the receiver has been separated out. So the RF source can be much closer to the backscatter and the receiver can be away. Right? When you do such things, suddenly people found that they can range of 130 meters can be obtained. Now that suddenly changes things because in modern communication, small cells are of small area. And here it is appearing that in a radius of 100 or 200 up to 200 meters, you will be able to communicate using the backscatter devices simply by using bistatic backscatter. That means you're separating out the RF source and the receiver. And people have demonstrated this with very small amount of power. They're able to communicate up to 130 meters. This has changed things. This is the way things will go because you can use very small amount of power and communicate very effectively. And also one other things, there's something called ambient backscatter. Right? In ambient backscatter, there is no RF source. You are simply using whatever signal is RF signal is there in the background. For example, there is a Wi-Fi router here around the room. The Wi-Fi router signal is picked up and this backscatter device is transmitting it ones and zeros on that. So the receiver picks that information up. You'll notice that there is a direct path from this ambient source to the receiver. There is also an indirect path. So there is some kind of a diversity thing comes. Those of you who are familiar with physical layer can quickly see that there is a different path. This is the indirect path and this is a direct path that can actually improve reliability in some sense, right? So backscatter, and this is called ambient backscatter, where you don't have your own RF source, but piggybacking on some other RF source in the neighborhood. Right? So ambient backscatter, people have demonstrated 500 meter range readily possible. If the RF source is close to you, you can happily communicate over large, and even up to 2.8 kilometers has been demonstrated when the backscatter device is very close to the source. Right? It is very, very energy efficient. And this is the way things will move as you move towards 6G. You are going to use a lot more of backscatter communication. One other technology. Are we supposed to take a break here? Oh, please stop me when we have to take a break. There's one other technology that we can use, intelligent reflecting surfaces. Right? So I don't know how many of you have. It's also called reconfigurable intelligent surfaces. They basically consist of metamaterials. All these things, these points, they're all made of metamaterials whose physical properties can change and are programmable by the microcontroller. Right? So it can be as simple a thing as something that is stuck to a wall. Each of these elements you can control carefully with a microcontroller, and that's about it. Right? So you have an intelligent reflecting surface, and you have a control board behind. Right? In a room at high frequencies, you can use it in a room. Right? On wall, you might have one of these devices in the room, and that can dramatically alter communications. And in cellular communication range, those type of frequencies, you can have it pasted on buildings, and that can change the propagation path and therefore change communication. What is happening here? I'll show you a figure maybe that can help explain this. You have an access point or a base station. You have this pasted on some building, let us say. OK, and there is a cellular user here. From here to here, the signal is very weak for some reason. Maybe you are using small amount of transmit power because you don't want to cause interference to others, right? Then what happens is these metamaterials, every one of these points, when a signal impinges on it, it will reflect with a phase change, right? What happens is the signal that comes, it will just transmit along with the phase change, right? When that happens, you can immediately see that those phases can be carefully selected in such a way that the signal coherently combines at this user. This and this path can coherently combine. And because the number of these devices can be very, very large, hundreds, it means that you can have hundreds of these elements. You can get very large improvement in signal to noise ratio at the receiver. Right? That is what it is. The G is this particular matrix. Right? And then you have a phase. Phi is the phase given by all these elements. And then this is HR. This plus H. So what happens then? And F is the beamforming. You don't have to worry about the math. The physical intuition is what you have to think about. By changing the phases alone, you're changing the propagation environment. This is very different from massive MIMO or MIMO. What are you doing in MIMO? You have a relay, let us say. You receive the information, then you transmit it again using a large number of antennas so as to exploit spatial diversity, let us say. Right? Here you're not doing anything like that. There is no decoding and retransmission. Whatever signal is coming, it is getting reflected. It's like a mirror. It's like having a large number of mirrors that you're able to control, right? Individually control using a microcontroller. The amount of power consumed at the intelligent reflecting surface is very, very small because all you are trying to do is to determine what the reflected with what phase change you have to reflect the signal. Right? Each one of these phases you're able to control. That's about it. There is no RF change, there is no power consumption really, right? But you're able to alter the propagation environment. The way in which the signal is propagating is changed. This is so fundamentally different from everything that we have been doing in the past, right? That is what makes it so exciting. So of course you have a problem of channel estimation. If you have to find out what the phases should be ideally, then you have to know a lot of channels and that becomes a problem. But people have found solutions for all these things. And performance in capacity, you can show increases linearly with the number of elements. So you can have large number of elements because these are very, very small. And if you have hundreds of these elements, you can improve the performance by a very, very large amount. For example, let me do this particular thing. I'll finish this and then we will talk of artificial neural networks in the replication. OK, so let us look at intelligent reflecting surfaces and its application. For example, suppose you have pasted this on a wall on some building nearby and you're transmitting from here, but there's a wall in between. OK, to a receiver. So obviously the signal from here to here is very weak, not good enough. But you can always program this intelligent reflecting surface and change the phase of each of these elements in such a way that you get very high signal to noise ratio at the receiver. And as you can see, you're altering the propagation environment. Also, you can provide more secrecy. Suppose you are trying to have a legitimate user here and here. This person is trying to eavesdrop on the communication. So what is it that you can do? You can ensure using these phases that the signal to noise ratio at the eavesdropper is very, very poor. So he will not be able to decode the information because of Shannon's theorem, right? The SNR required to decode the information at that rate. They'll ensure that it does not have simply by adjusting the phases of the intelligent reflecting surfaces. Now, you can improve the signal to noise ratio of the user at the cell edge. You can also do massive device-to-device communication. This wants to communicate to this wants to communicate to this, and so on. All this is possible using by adjusting the phases of this thing intelligently. It's also possible to have these pasted on roofs and walls of a room. And you have a large number of, you have an access point or something in the room and or a router, some RF transmitter in the room. Then these phases are so adjusted so that all the IoT nodes that need energy can get the energy. Right? You beamform towards that and they can harvest the energy. Right? So as you can see within a room, you can alter the propagation paths and the way the signal propagates. So this is a very, very powerful idea. This idea has been generalized. People have built intelligent reflecting surfaces already. Companies have manufactured it and demonstrated. It is a very powerful idea in general. If you think about it, suppose you have a large number of rooms in your college, let us say. Every room, let us say there is a Wi-Fi router. So obviously, because you're using the same ISM band, it will not work very, very well because your same band is being used. There's going to be a large amount of interference. But suppose the walls are programmable. People have made programmable walls. What does the programmable wall do? The wall like this. For example, what do? You can make it, you can ensure that certain frequency bands can pass through and certain frequency bands cannot pass through. If I'm having a Wi-Fi router here and here, I'll program this wall to cut off the 2.4 gigahertz band. So I can have a Wi-Fi router and communicate. I can have a Wi-Fi router here and communicate, and yet both of them will get high rates because the wall is blocking that particular band, right? So think of the possibilities. If you have a large number of rooms, I can carefully control each of the walls and ensure that I can allow certain frequencies to pass. I can make certain walls transparent to certain frequencies and so on. So this is a very, very powerful thing. And such things have been built using metamaterials. They have built all these things and readily, although commercially it's not readily available. Companies have tested and demonstrated. So for those of you who are interested in research, definitely this is a very, very good topic. So next I would like to talk of artificial neural networks. Are we supposed to take a break here at this point? Would you like to take a break of 5 minutes?
Yes, sir.
Okay. So if you have any questions, you can ask me, or we can go in for a break. Or you want to have to ask the questions in the end, either way. Okay, so we'll take a 5 minutes break. And exactly at 8:30 we can raise them. Please let me know when I can start. Can I start now?
Yes, sir.
Yes, sir.
Okay, fine. Thank you.
Yes, sir.
Sir.
We can start now.
Yes, sir. Please.
Okay, so right now we'll talk a little bit about. I talked about various things. I talked about most communication aspects, right? And we'll talk a little bit. And I did not get enough time to talk of underlay type of communications and how power control can be used. We had less time to talk about it, but I think it's okay. We used underlay cognitive radio power as power controlled technique in order to enable communication, right? Good, high quality communication, but I'll come to that a little later, maybe if you have time. So we look at artificial neural networks and the use. I think all of you are familiar with neural networks, right? We have input layers, hidden layers, and output layers. We have connections. These connections, I think all of you are familiar, are just weights, and all that the neural network is doing is implementing a certain function. It's basically a function approximation, either for prediction, regression analysis, and so on, or for classification, or for data processing, right? So I think all of you are familiar with this, right? This is just a, and obviously the way in which the weights are determined using training, right? So you have some training data, and so this is very well known. When you have a deep neural network, you have a large number of hidden layers. You can implement more complex functions better, but as you are aware, and signal need not move in one direction, you can also go back and forth and so on, but they require a large amount of training data simply because of the fact that the number of connections, they are large, number of weights to be determined are very large, huge amount of training is required. The other disadvantage they seem to have is that there is no real physical insight to be gained from the solution. That means you have a solution that works, but you cannot get much insight. You cannot clearly explain why it is working, which is not a good thing, because any solution to a problem should also give some fundamental insight into the problem. But that won't happen in a deep neural network, because all you're doing is training and then running it and hoping for performance improvement. Right? And the other disadvantage is that in wireless channels especially, it's a dynamic environment. Many situations, for example, the channels change because of fading. The number of users who are present can change. IoT nodes, so many IoT nodes can suddenly start transmitting. The number of nodes transmitting can keep changing, right? It's a dynamic environment. It's not static. So the performance of these deep neural networks might not be very, very great, right? So I'll skip this. It's already been done in the different. OK. So I'll be talking of this. Then I will also, but I need to talk about a little bit of something called non-orthogonal multiple access, because I will be talking of deep neural networks or DNNs in the context of non-orthogonal multiple access, right? So it's important for me to first explain what non-orthogonal multiple access is. There is something called orthogonal multiple access. It means that that is what we have been doing, right? From 2G to whatever up to now, whatever we have been doing is just that you have one frequency, you have one channel resource, right? That can be in the form of a frequency. For example, in OFDM, it can be one carrier, or it can be one time slot, time division multiplexing, or it can be one code division multiple access. You have, right? See, So it can be a code or frequency or time you are transmitting, right? So orthogonal multiple access simply means one channel resource of some kind is being used for transmission by each user. Now, why is it that this can no longer work when you go ahead? Simply because the number of devices has now become 10 million devices or more per square kilometer. That means the number of devices that you are dealing with are very, very large. If you have 10 million devices, can you talk to each and every one of them over time? It is not possible, right? It is simply not possible to have orthogonal type of channel resources allocated to each of them. When you're having a dozen users, you can give them all orthogonal codes, or you can give them different carriers and allow them to communicate. When you have 10 million devices, that you can no longer have this luxury, right? You cannot allocate orthogonal multiple resources to each of them, which means that you must allow large number of them to communicate in the same frequency using the same channel resource. If one carrier is being used, that same carrier multiple users are going to transmit, and somehow we should be able to decode the information correctly. Right? So non-orthogonal multiple access is one way in which we can do it. What is done is you transmit in the downlink, for example, you transmit a weighted sum of symbols. At the receiver, you perform something called successive interference cancellation. Right? It's not very complicated, but there's a history to it. For those of you who have been following all the standardization process, lots of people call essentially the same thing but different names because they're from different companies. They've all been trying to push it. Ultimately, anyway, it was accepted in 2015, right? By the standardization body, 3GPP, and so on. Right? So basically, we're going to talk of NOMA. Let us explain the basic idea of NOMA, how it works. You have a base station, okay? There is one user who's close by and the one user who's far away. So what is the characteristic? You know the characteristics of feeding channels, and you know the characteristic, the path loss type of thing, right? So you know that a user who's close by will get a signal to noise ratio that is large very often. This user is going to get a poor signal to noise ratio. The quality of service for this particular user is too poor. He won't be able to communicate. So what do? You want to communicate to both of them. You pick one strong and one weak user. Okay. And you try to communicate to both, but you're not given different frequency bands. You're not given different time resource or a code resource. You're multiplexing based on power, right? So what you do is you transmit weighted sum of symbols of user N and user M. When you transmit a weighted sum of symbols, this one, user M, will treat the other user's symbols as noise and decode it. What you're doing, the user who is far away, but the channel is weak, you allocate more power. The user whose channel is signal to noise ratio is good, channel is very strong, you allocate less power. Right? So in some sense, you're sacrificing performance of a user who's close by because he already has good performance, and you are using whatever power that you have and you're allocating more power to a distant user. Right? This user, because more power has been allocated to user M, its symbols can be decoded by treating the user N symbols as noise. And what does this user do? He'll have to do something very different and special. He cannot decode his own symbols. Why? Because you're transmitting a weighted sum of symbols and user N has got less power, so you'll not be able to decode. What you can do, however, is that you can decode the stronger user, that means symbols of the stronger user, user M, right? And then after you detect, you can cancel the interference and then decode the symbols of user N, its own symbol. So the near user has to do SIC. Basic idea is that. So you're multiplexing in this particular way. More power is allocated to the user who's far away and less power to the user who's close by. And you're multiplexing symbols in the power domain. Okay. So when you have large amount of power, you can do this because this way, of course, here I've drawn it for two users. You can show that you can communicate like this to a large number of users. So you want to send, let us say, software upgrades to a large number of IoT nodes. You can send it to a large number of IoT nodes, or you can set parameter setting you want to do. You can do it for a large number of IoT nodes concurrently. You want to send this, right? So this thing can be done. and in the same frequency band simply by multiplexing in the power domain. This is possible because the data rates that you are desiring for IoT communication is actually very low. It's not very high, right? You're not aiming for high data rate. What you want is low data rate, but to a large number of users. So multiplexing is the way. So non-orthogonal multiple access will enable you to do that. And why does it work? Let me give a very basic intuitive idea, right? Let us think of two different techniques. OK, one of them is called orthogonal multiple access. You have divided a frequency band into two parts. Half of it you're using for near user, half for far user. OK. Frequency division multiply. What happens now? What is the Shannon's formula? What does it tell you? Capacity is W into log to base 2 of 1 plus SNR. SNR also is a function of the bandwidth, but it's within the logarithm. So what is important is it's a multiplicative factor of W. It plays a very fundamental role, right? In this particular example, the capacity is going to become half approximately simply because of the fact that you have a multiplicative factor of W, which has now become W by 2. What happens here in non-orthogonal multiple access? This continues to remain W, but this will reduce a little bit. It doesn't matter because it's within the logarithm, right? Hope you're understanding the basic physical idea why this thing works, right? You are ensuring that this multiplicative factor is not spoiled. You are decreasing your SNR a little bit, but that has less effect and you can still decode and you can have good capacity. So what you do, I think you first try to, I think this we already discussed, right? The rate regions and so on. For those of you who have done information theory, will be able to appreciate. OMA gives you this rate region and non-orthogonal multiple access can be a much better rate region. That means the rate tuples that you can get will be much better with NOMA than with OMA. OK, so this can be used, for example, if you have a base station, you have a large number of users. You can communicate to a large number of users in the downlink. And similarly, large number of users can communicate to a base station concurrently using the same frequency band in the uplink. Right? In the uplink, how do you think it takes place? It detects the user one stronger one first, then next stronger one. It keeps on canceling the interference and then trying to decode each of them successively. Right? So both uplink and downlink it has been applied. Of course, the problem is that of power allocation, even in the downlink. The amount of power that you allocate for this user and the power you allocated for this user has to change. Similarly, for large number of users, if you are trying to transmit, power allocation is you have to determine very intelligently so that all of them can receive the data successfully. Using channel knowledge, suppose you know all these channels that can be used very effectively to control and you can improve performance. Right? This is all well known. You can select a subset of the users. You can do power allocation very intelligently. The non-orthogonal multiple access can be made to work very, very well. So the basic idea, of course, cooperative NOMA also, let me discuss if I have figures. So yeah, I have a figure here. So you have a base station, you have a near user, you have far user. But suppose you say that I will pick one near user and one far user. That means I'm trying to communicate to both of them. I can generalize this idea, of course. So now what happens is you're trying to communicate to a far user. And this near user can decode both the symbols. It has to decode the far user symbols first anyway, then it will decode its own symbols. So it has got information about the symbols of this far user. Right? So it makes sense for it to relay the information in the second phase. And this can do combining and therefore improve the performance of the user at the cell edge. Right? So this is called cooperative NOMA, where a near user will, which has already anyway has that information, can pass it on to the, can relay the information to the far user, and this can combine this and therefore get diversity advantage. Okay. So people have proposed a pick the best user here and communicate. What we showed is that there may be a better way. We came up with a better user selection mechanism such that with n users here and f users here, we're able to get a diversity of n plus f for the far user. That's a very big deal, right? Improving the performance of the far user dramatically. The users at the cell edge, we can improve the performance dramatically simply by doing more intelligent user selection. What they were getting earlier was diversity of n and f. we're getting a diversity of n and n plus f. So see, this is what I'm saying. Here you get same diversity, and later on, whatever the student had done, we're able to get much better diversity performance for the far user. Right? By increasing the number of near users, is improving the performance of the far user. This is a big deal. So a lot of variations of this norma, of course, have appeared. We ourselves have worked on non-orthogonal multiple access and underlay networks. But I don't know whether we have a figure. Maybe I can use that. Do seem to have it somewhere. I'll come to it. Right. We also applied it non-orthogonal multiple access using relays for D2D transmissions and so on. So in underlay cognitive radio, okay, for example, relayed norma. You have a base station, you're relaying, is transmitting symbols of both the users concurrently, near and far. The relay decodes both and then relays it to both the near user and the far user. You can also have many such NOMA networks are possible. We also worked on something called CDRT, right? Coordinated direct and relay transmission. Okay, you have a relay, you have a near user and a far user. See what those of you who have done a little bit of wireless communication will know that if you have a distant user, its performance is weak. Suppose you add a relay in between. So you have this direct path and a relay path. So diversity of 2 you can get at the far user, is it not? Right? But you're communicating only to one user. The basic idea of NOMA is to communicate to more than one user. So what people have said is that yes, I'll communicate to a near user, then I'll communicate to a far user through the relay and get a diversity of 2 here and a diversity of 1 here. Okay. What we said is that we can change the way we are doing signaling and way we are doing processing at the near user to get a diversity of 2 both here and here. Right. So the power that we're allocating to the near user can decrease. More power is allocated to the far user and far user performance improves once again. Right. So this work was published in TCOM, Transactions and Communications recently. Core idea is very simple. We're able to communicate to 2 users and get low outage at both the users simply by doing more intelligent processing at the near user. We also did the same thing for underlay networks. I don't know whether I have a figure. It would be great if I have a figure actually. Apparently I don't have. Yeah, I think here we have this is a primary network and this is secondary network, right? So we said that, OK, yes, we have a cooperative NOMA type of network, a near user set and a far user set. And what I told you about underlay cognitive radio, right? I told you that the transmit powers will be random. Why they're random? Because the amount of power with which you transmit has to vary to ensure that the interference caused to the primary user is a fixed quantity. Let's say ITL is IP. So you cannot cause more than IP amount of interference here. So you have to adjust your transmit power accordingly. So the transmit power keeps varying. You cannot transmit with any amount of power that you have. So when you can't transmit with large amount of power, does it make sense to use non-orthogonal multiple access? Power division multiplexing. Does it make sense when you are power constrained? It is intuitively you think it is not true, but it turns out that if I can perform intelligent user selection, right, and I'd use adaptive techniques and switching, then it is between various modes, right? Signaling modes, it actually makes sense, and non-orthogonal multiple access, power division multiplexing of symbols actually works even in this power constrained scenario. This is what was the achievement. We can show that it makes sense even when you are power constrained. The way it works is like this. Sometimes the base station has large amount of power. When it has good amount of power, you communicate to both. When you have small amount of power, right, then you switch to cooperative NOMA. Then this decodes and then forwards and so on. Right? By switching between the modes and selecting the users intelligently, we're able to get very good performance with non-orthogonal multiple access, even in a power constrained scenario. OK, this work I will not go into too much detail. The idea was to give an intuitive picture we're able to show that I don't know, those of you who have done a wireless communication course will know that the slope of this outage curve will give you an idea of diversity, right? So we're able to show that we're getting much better slope. Okay. Obviously, you're also getting much better throughput. Okay. I will skip some of these details because I think they were not. We also worked a little bit on something called the grant-free access. I will maybe talk a little bit about it because it might interest you. We worked also on underlay NOMA with uplink. So your uplink information is being transmitted by a good number of users in an underlay network. Other thing that is important in modern communication is something called semi-grant free communication. It means that, so normally I don't know, I think I have a figure here that explains to you how signaling takes place. Oh, apparently not. How do you do signaling in a practical system? Right, so there are a large number of users. Each user has to, I think I have one figure maybe here somewhere. And 1 second, please. Yeah. So IoT device wants to transmit data. What does it do? It listens to the base station, the DL sync. It sends an array preamble. You get an array response. You get a connection request, send a connection request, wait for a connection resolution, keep on repeating till the connection resolution is obtained. Then you transmit your data and then you wait for the acknowledgement of the packet. But if you have to do this with 10 million devices per square kilometer, that is not going to happen, right? So what we do here is that IoT nodes will simply listen to the DL sync and shoot data whenever it has. What is the disadvantage of that? If large number of IoT nodes shoot data in the same slot, obviously the packet is going to be lost because of collisions, right? So you will get a you will not get a no acknowledgement. Then you retransmit the packet and hope for an acknowledgement. So this is called grant-free access. You're not waiting for the base station to give you a grant for transmission. You're simply shooting data, right? So obviously it has to be reliable because these IoT nodes also have very low power. You cannot keep on retransmitting a packet. So intelligent use of the signaling is very, very important. But the difference between grant-based and grant-free, you have to appreciate. Right? Grant-free does not require much signaling overhead. You just wait for synchronization and then you shoot your data and then hope for an acknowledgement. Okay, so let's go back to this. Okay, so we looked at situation when you have a large number of users. One user is transmitting to the uplink. At the same time, a lot of IoT nodes are also trying to transmit in the uplink. Here we used underlay cognitive radio principles to manage the interference by saying that yes, when user is transmitting, I know that with a very high probability, the SNR that he has at the access point is going to be larger than what is required because G is the channel, right? And we know it's a fading channel. For a certain quality of service, we know that the signal to noise ratio is going to be larger than what is going to be required with a very high probability. So there is ability to tolerate interference. Now it's only a question of, OK, I have an interference of I that I'm able to tolerate. The question of how much interference can this user cause? How much can this cause? How much can this cause? So that the overall interference does not exceed I. Right? That is called apportioning of interference temperature limit for massive mission type communication. We showed that with 2 users, you can see the SNRs. And we can show that by carefully selecting the apportioning parameter, we can get good performance at both the users. And also have patent application on this to show. Anyway, the point is NOMA also requires optimization. That the type of power control, you're transmitting a weighted sum of symbols. Those weights have to be very carefully controlled. If you have CSI, channel state information knowledge, that can be utilized very, very well. If you can select users very intelligently, then you can get much better performance. Then you can also select users to improve node level energy consumption, minimize the energy consumption at the nodes, and so on. So there's also the issue of fairness, right? which user gets performance. Users who are close by are getting much better channel access. Those who are far away are not getting access, and so on. So these things can be taken care of. So then how do we schedule? Which user do we pick for NOMA transmissions in the downlink or the uplink? Right? How do we perform such selection? Right? All these are difficult problems. Why DNNs should be used? Deep neural networks need to be used. The reason is that networks are becoming increasingly complex, right? And when you cannot, conventional methods and optimizations cannot really work anymore, right? We think about it, the number of machine type devices, that means IoT type of nodes, etc., not cellular, radio, human mobile devices, but other machine type devices that are increasing because we increase use of smart cities and so on. The number of, and in Industry 4.0, the number of IoTs and others is going to increase, and continuously it's going to explode, going to increase. When that happens, you have to handle a large number of users, and therefore DNNs become very, very important. For example, suppose I use intelligent reflecting surfaces, which makes sense in such situations. Then you need to control the phases that each element is using in such a way so as to maximize the performance of, and to ensure performance of large number of users. Right? So suppose there are a large number of wireless networks utilizing the same band, that you have to ensure they all have different quality of service requirements. You have to meet the quality of service requirements of multiple networks using the same frequency band. That is, for that, it's a very complex thing to do. Complex optimizations need to be done. Therefore, DNNs are useful. The other thing that you can immediately see is that when you are going to use the same frequency band for transmission by multiple users, there is going to be interference. And this interference has to be very carefully managed. And this is a very important because frequency reuse has become one. You're trying to reuse the same frequency multiple times the band in the same cell. Then obviously you have to manage the interference very, very cleverly. And for that, we need complex optimizations. We need DNNs, right? The other reason is that when there is large amount of interference, for those of you who have done communication theory, you'll know that when the noise is Gaussian, all the receivers, we know how to make it work. We know how to optimize the performance. But the moment the noise becomes non-Gaussian, the receiver, how to build a receiver, etc., is difficult. It is not always known, and therefore DNNs become attractive. DNNs are also attractive because the channel estimations that you get are imperfect. Right? You need channel estimations at the receiver, right? Without knowing the channel, estimating the channel, you cannot do. You cannot build a receiver. You cannot decode. Right? So, but because these are imperfect, and you have non-Gaussian noise interference, therefore DNNs should be used. The other reasons are, as you keep the size of the nodes is decreasing, the number of nodes is increasing, they're going to become increasingly low cost, right? They may be doing direct conversion from the 1 gigahertz to the baseband, right? When you do such things, they become low cost devices, right? Direct conversion can take place. In such cases, IQ imbalance can exist, circuit imperfections can exist, and all these can make receiver design very complicated. So DNNs can then be used as at the receivers to alleviate this problem. So also transceiver optimizations, right? When simple network, we're able to optimize the performance of the transmitter and the receiver. We're changing the parameters together to get the best possible performance, to get the best possible energy efficiency, right? But when the systems become more and more complex, it is no longer possible to do that. Therefore, we need to use DNNs. And also, for example, when there is traffic, right? Suppose you have IoT nodes, they all have their own traffic patterns. And if you're able to predict traffic from each of these nodes, then you can provide grant-free access in a much more intelligent way. You can use the channels in a much better way. Right? And I think the other thing is NOMA with caching. I don't know how many of you are aware that commonly used packets, when you have at any given point of time, people are clicking on some links and downloading some web pages. Commonly downloaded web pages
are there. Many people click on the same web pages, which means that those common nodes can be stored in a nearby. You don't have to access the base station for that. It can be stored nearby. And then you can use non-orthogonal multiple access with caching to improve performance. For those who are interested, can read up. Then what are the challenges with DNN? You require huge amount of training, very difficult in communications. And what should the input to the DNN be? Any DNN requires input. What are the input? What should give us the input to the DNN? That is something it's a question of design, right? How you go about doing things. And as I already told you, the different type of networks are coexisting. When you have a dynamic environment, they all have to require careful optimizations. Sometimes operators may not be willing to share data, right? So it is not easy to, but there are challenges therefore in DNN because DNNs require sharing of data. The computational power is also a problem because to implement DNNs requires battery energy. In a battery power node is not very practical, right? Optimization of the system as a whole requires sharing of data, but channel bandwidths can be a bottleneck. You want to share data, the bandwidth is limited and therefore it becomes impractical. So all these are difficulties. So let us look at use of DNNs in the physical layer. Then I will talk of DNNs in the other layers, right? For example, for channel prediction, interference mitigation, etc., we can use. Right? Then we can talk of jointly applying the machine learning for joint optimization of encoding, modulation, waveform at the receiver and transmitter, etc. We can waveform design and so on. We can do. Third stage, knowledge of existing models can be used to decrease the training required. So large possibilities exist with DNNs. So look at physical layer. We can use DNNs to optimize code lengths, right? To minimize latency. Synchronization can be done. You can compensate for imbalances. I told you, either lack of synchronization, you can compensate. You can also use localization can be done using DNNs. You're basically you're looking at RSS, right? Received signal strength, and you have fingerprint based DNNs for localization. All these things are available, so you can look at literature. I told you that when the noise becomes non-Gaussian, non-stationary, non-linear environments exist, DNNs need to be used because it is not mathematically tractable, right? You want to do channel estimation and equalization together, DNNs again become useful. Beamforming, etc. There are many situations when physical layer, when DNNs become useful. In MAC layer, for example, you want to do resource allocation. Right? You have a certain number of frequency bands allocated to you or time resources allocated to you. How to allocate it to different number of users, how to pick users when you're doing non-orthogonal multiple access, how to do user pairing, right? Which users to select as near user, which to be far, how to come, which near user should be paired with which far user and so on. How to select users, which users should receive data concurrently in the downlink, which users should be allowed to transmit uplink in the uplink concurrently. What modulation scheme should they use, right? And all these things can be determined using DNNs. How to allocate the transmit powers? Because you want to minimize energy consumption of each of these nodes, right? These are IoT nodes, they don't have power. How to intelligently control the transmit powers? All these are MAC layer issues. Let us look at certain issues. I will look at certain problems for multi-user detection using deep neural networks. Let us look at K users transmitting in the uplink. OK, so there are K users that each user is transmitting with the power of P, PK. The channel is HK, the symbol is SK. So you're getting a weighted sum of symbols. A large number of users, K users, are transmitting simultaneously. Each user has, the Kth user has got a channel HK to the access point. So that its symbol SK is multiplied with HK. It is transmitting the power PK, right? And therefore the sum of all these is appearing. In the air, they will all combine, right? And at the access point, you get a sum of all of these. This, of course, is after match filtering and sampling and so on, right? This is understood. Demodulator output is what this is, right? Now, what is your job? Your job is to find out all these SKs. First of all, why are the K users? because of the fact that you need to have more large number of users transmitting the uplink concurrently. The K users are transmitting, and now we have to find out what all, if only one user is transmitting, we can happily decode. It's simple and straightforward, symbol plus noise, you can decode. But if large number of users are transmitting, you have to do something called multi-user detection, right? You have to detect S1 to S of capital K. Multi-user detection techniques are available. You can look up in literature. Many different types exist. You can also do something called successive interference cancellation. How does it work? Strongest user is picked. Decode that by treating all other users as interference. After you estimate that symbol successfully, cancel it out. Why? Because suppose the first user is estimated, then P, you can take this R and subtract square root of P1, H1, S1. Can we subtract it? Then you'll only have K minus 1 users. Then estimate the next one. Cancel it like that. Successive interference cancellation can take place. Similarly, we can have something called parallel interference cancellation based on the same ideas. Right? So these multi-user detection techniques can be used. So what is the basic idea of multi-user detection? There are capital K symbols, each of them from a alphabet of size equal to S. Suppose it is binary symbols, then 2 power K possibilities exist. Are you able to see that you're having capital K symbols, each of which is binary? The number of possibilities is 2 power K. Now you're receiving something, you have to classify it into one of these 2 power K, then you'll get the sequence of symbols, the entire set of symbols you can get, right? So basically then it's a mapping. It's a mapping from R to one of these S power K levels. So you have, in this particular case, I only got 2 because I have taken binary case and I've, right? So I made the problem very, very simple. So I got an output 1 and output 2. So I have a NOMA signal. I'm doing certain hidden layers and output layers are there, and I'm getting 2 different outputs. Right? It's only for 2 users. It's very straightforward. Of course, large amount of training will be required because they're going to have large number of hidden layers, which I have not shown. Right? But the idea is that I'm treating multi-user detection as a classification problem. Then I'm saying yes, a deep neural network is actually a function that maps from the received signal to each one of these outputs, and it's you're making it work as a classifier. So one of these is going to get picked, and that will tell me what symbols have been transmitted. Right? Now, obviously, large amount of training is required, but if you can exploit the inherent nature of the signal, what's the nature of the signal? It is the sum of many signals, right? The sum of many. So what you do? Suppose I take a NOMA signal, apply a DNN for output 1. I feed this particular output to one of these layers of these networks. What does that do? Effectively, you're canceling it out this, right? Because you know that once you cancel out output 1, all that you will have is signal corresponding to output 2. Then you can have a DNN here and you can get output 2. What's the advantage of this? This DNN is you have 2 separate ones which are interlinked, but they will all be smaller size, and therefore training can be much faster, right? You can have much smaller training and you can get good performance. Right? Basically, these are model inspired DNNs. What this is inspired by successive interference cancellation ideas. Right? This DNN you can show will work much better with a non-orthogonal multiple access. So if you have multiple users, let us say large number of users are there, you're treating it as a classification problem, but you're not applying multi-user detection blindly. You're trying to use successive interference cancellation based ideas in order to decrease the complexity of the DNNs. Similarly, you can use a parallel interference cancellation based DNN like this. You have a NOMA signal, you have DNNs here, you have a DNN here, and you can do message passing between the layers. By getting certain amount of information about this output here and this output here, you're able to improve the performance, and this is called parallel interference cancellation inspired DNN. You can have this structure and you can get good performance with much less training. You're able to implement. It will obviously have low complexity. So DNNs do find use in detection type of problems. Okay. Now let us look at one more example
to do that, I'll have to explain something called over-the-air computation. Sounds complicated, nothing much to it. But suppose you look at various nodes, okay? Let's say they're all temperature sensors and they're transmitting the temperature. And what you want is the weighted sum of these temperatures. What can you do? You can modify the weights and transmit these temperatures. One thing you can do is to make each one of these temperature sensors transmit information to you one at a time. Very, very slow, right? Large number of nodes are there. It's going to be very wasteful of bandwidth. What you can do otherwise is to take a weight. You can multiply with them with such weights. These weights I'm choosing a WK by HK because the channel is equal to HK from the kth node. So when I multiply with HK, this cancels out. You get WK into XK, and then you'll sum of all these will come. In the air, they will all combine, and what you will get is a weighted sum of temperature measurements. That is what you want. That means this is called over-the-air computation. So in one single time slot, simply by changing the weights, all the nodes have transmitted their information to the access point. So it is very effective use of the spectrum. This is called over-the-air computation. Now we will see how this over-the-air computation can be used along with DNNs to improve performance for cellular backhaul. Right? So large number of nodes are there. You have access points. I think this is, you have multiple access points. OK, this and this. So you can look at users. You'll find that signal from each user can go to multiple access points. Suppose you go the conventional route. How do things work? This access point will get information from all of these, decode that information, and send all the decoded symbols to the CPU. OK, this obviously is going to be very wasteful for many reasons. First of all, the same user may be connected to two of them, may be decoded by two of them. Redundant information is sent to the CPU. It is very wasteful, and the amount of time it takes to send information is very large because you're sending them one at a time, right? So we need to do something different. What is done is like this. At each of the access points, we're going to have a DNN, right? And at the CPU, again, you have a DNN. So what you will do is to implement a certain function on the received signal. Then you transmit it, and the CPU apply a different function, and you decode all the bands. And this is done by over-the-air computation. All the access points transmits concurrently and not one at a time. So you can save a lot of bandwidth. OK, let us look at this. It takes a little time to appreciate what I'm saying. Suppose APs have n antennas. I don't know how many of you are comfortable with multiple antennas, but if you can see, it's a vector of channels now, not just one. It will become h of m comma k. And then you have power pk is being used. You're transmitting sk, and this is the noise. This is what you receive. Okay. What is the classical approach when you have multiple antennas and you're trying to receive from multiple users, k users? Right? What is the conventional approach? Zero forcing, right? This is not the way, because this is, you can apply zero forcing such that a particular, let us say, W Hermitian, something you apply beamforming weight such that multiplied with HMK, one of them is equal to 1. The rest of them that multiplied with other HMKs will all be equal to 0 or close to 0. So you will get one of the symbols. That is called zero forcing. And this is very wasteful in many different ways, because you'll decode all the symbols and you're going to send one at a time. Each of these access points will send to the CPU. And unfortunately, the same set of symbols may be decoded by different access points, and then you're sending redundant information. It's wasteful again. So use of orthogonal resources is important. So what we do for that, you use these particular weights. OK, beamforming weights are used. OK, so and what you receive is like this. What you receive RMK will be like this. You're using some beamforming weights and you're getting RMKs. So each of these users, you apply MRC and you take HMK Hermitian into whatever you receive, you get this. OK, now you take each of these RMKs, you quantize it using alpha bits to obtain R tilde. OK, So what you do with this R tilde, you transmit all this R tilde by over the air computation using normal principles, and you get RK. And the CPU will decode all these symbols using RK. What is the advantage of this? Redundant transmissions have been avoided. But RMKs that you're getting are all correlated because they are weighted some of the same set of symbols. Same set of users may be appearing at various access points, and therefore you're transmitting redundant information. It's a total waste of the best. What you can do instead is something like this. Suppose each access point can use an encoder function, a DNN, to compute based on the received signal and knowledge of all the channels and the powers. You can apply a DNN to get certain AMs. OK, and then you can use over the air computation to transmit all these AMs to the CPU. The CPU applies a DNN. I'm calling it a certain function G, and based on Z and all these Q1 to QM, these weights are known. And then you try to estimate S1 to SK. This DNN based implementations are very, very efficient. They're treating the over. Yeah, so obviously you can train all these DNNs together in order to get good performance. This obviously is very, very good because the amount of time required, you are just whatever received signal that you are getting is a certain, you're applying a DNN, getting AMs, you're using over the air computation in one shot. All the access points are M access points are communicating to the CPU, right? And the CPU applies a DNN in order to estimate the symbols. So the bandwidth required is very, very small. So as you can see, DNNs can be utilized for multi-user detection, and we can change the structure so as to improve the performance with the DNNs. Right? Structure can be modified to suit the problem, SIC inspired or PIC inspired, or you can apply these deep neural networks for cellular backhaul in a very intelligent way to decrease the amount of bandwidth required. You can also apply to massive machine type communication. Here, I think you might see the large number of nodes. You're transmitting with various powers and various resource blocks. So you'd see multiple nodes transmit with the same resource block with different powers. It is fine, right? The moment these devices transmit with same power, then it's going to become an issue, right? If the two users transmit at the same power, it is not going to work out because you'll not be able to do SIC, and non-orthogonal multiple access will fail because it is based on using different powers, right? So this one and this one are using the same power, P1 and P1. So these two, the packet is going to be lost in that resource block, right? Because there is a collision. Now the question is how to decide on which users, how to predict the traffic in order to improve your multi-user detection techniques, right? These things are very important. We're running a little short of time. So DNNs can be used to select uplink users in a semi-grant free scheme. That means you can select which users are allowed to transmit to the uplink. Machine type devices can be transmitted in the uplink, right? This is something like a semi-grant scheme, right? They're not taking permissions, but some of them are allowed to transmit and some are not allowed to transmit, and you can use DNNs for that. You can minimize the chance of collision by predicting data transmissions. That you can do, right? If you're monitoring the traffic patterns, you can use DNNs for that. And if you monitor the MTD traffic patterns, then you should be able to minimize the chance of collisions. And each one of the DNNs, so suppose each one of these users have different quality of service requirements, you can meet all those things using DNNs. You can group users intelligently to minimize loss of packets and so on. Even when you do NOMA with caching, here also we can use DNNs to decide to predict the files that will be sought by users. So whichever files are going to be sought, very packets are going to be sought by a large number of users, you can keep it locally and not access the base station. Right? And you can minimize the cache miss probability. For those of you who are aware of how caching works in communication networks,
So you notice the large number of users are downloading the same page. Those commonly downloaded pages are stored locally, and therefore you minimize the chance, right? But you can use DNNs to decide which packets should be stored because you have finite amount of storage space, right? So decide which packet should be stored and how to minimize your cache miss probability. Chance that you have to access to the base station and not locally, that you try to minimize. For example, when you try to use intelligent reflecting surfaces in order to communicate to a large number of devices, here you have to change the phase of all these elements in such a way as to ensure that all these nodes get acceptable quality of service. In order to do that, you have to determine the phases, and that is not a simple task. It's a complex optimization problem. So this can be done using DNNs. Similarly, I was giving you an example of how the propagation environment can be changed. Your walls can be programmable in the sense that you can decide which frequencies can pass through and which cannot based on metamaterials. And that if it is done, then DNNs can be used to decide which frequency band should pass through which walls and so on inside intelligently so that you can get best performance. Right? So as you can see, energy, we talked about many things. We talked first about energy efficient, how to manage using energy harvesting. Then we said that, how to combine energy harvesting with battery energy. Right? We talked of buffered nodes and energy buffers. Then we said that energy efficient signaling is the way to go because the way things are, when you move forward, you're going to require self-sustaining nodes that require no batteries. And that is only going to be possible if you're going to use energy harvesting. And if you're going to use energy harvesting, you need energy efficient signaling because conventional signaling techniques are no longer can be used because the amount of power they require is too much, right? Then intelligent battery energy management is very important in the short term because right now we cannot build self-sustaining nodes. So at least we can use intelligent battery energy management to prolong the lifetime of the node. Then we need to have better protocols to save battery energy, and spectrally efficient signaling techniques need to be designed for MMTC as well. For all these things, we found the DNNs will find great use, right? How to determine the phases of this in order to even to perform simple non-orthogonal multiple access. DNNs can be very, very useful. That is all I have to say. If you have any questions, you can ask me.
Any queries from the participants? Any queries from the participants? Okay, I request all of you to switch on your video. We have to take a group photo for today. Kindly all participants switch on your camera. Sir, can we take a photo of today, sir?
Sure.
For screenshot, I have to take, sir.
Yeah, fine. Yeah.
Please, all of you switch on your cameras. Sir, can you move some other slides, sir, instead of thank you slides, so that I can.
Yeah, sure.
Yeah. Some diagram. Yes, sir. Yes, sir.
Okay.
Okay, sir. This is okay.
Okay.
One second, sir. It's loading. Okay, thank you so much, sir, for the informative lecture today on the topic Introduction to AI for 5G/6G networks. I'm sure that today's lecture will be the base for the forthcoming lecture sessions. And we thank wholeheartedly on behalf of Vailtech University. I render the thankful heart to you. We like to have touch with you, sir, and for spending your valuable time this evening time. It's really tough speaking for 2 hours continuously, and you have made this day a successful one, useful one to the participants. Hope many of the participants are doing their research. So surely your expertise and your experience on the many projects will help them to carry out their research also, sir. Thank you so much.
Pleasure to
Thank
join.
you this evening.
Thank you for the invitation.
I thank all the participants also for joining today. And tomorrow's session also will be starting the same time, 7 p.m. tomorrow. Thank you, Dr. Shankar, sir. And we wish you all the great success in your life also, sir. We pray
Thank
for
you very
you. We
much.
thank
Thank
you
you.
so much.
Thank
Yes, sir.
you.
I'll contact you over
you.
phone, sir. And
Oh,
thank you so much.
Sure.
Thank you,
Okay.
sir. Thank
Good night. Thank you. Bye.
Thank you, sir.
Thank you, ma'am.
Thank you. Thank you, all of you. Thank you, all participants.
Thank you, ma'am.
1 second, I'll download the attendance. அனிஜா அழகா தெரியுறீங்க கேமரால.
Man, stop recording.
Yes, yes. My system is very slow. Okay, thank you, all of you. You may leave.
Thank you.
Thank you, ma'am.
Thank you.
Thank you, ma'am.
Tomorrow, all of you, please join on time.
Ma'am, sorry to disturb you, ma'am.
Yeah,
Feedback link in the group.
Please post the feedback in the link given. All the participants, please.
Where is the feedback link, ma'am?
It is posted in the